about the fatigue. Today's topic is fatigue in EN 13001, Eurocode, FEM, DNV standards, and the others which are implemented in our program. We will show everything on the model of ship-to-shore crane, which is designed in Femap. Last one was in Ansys. On reporting, today we're going to show it in Femap. This is a very beautiful model prepared by our engineers. And but I want to let you know that everything I show today is available in all the solvers we support. So it's available for Ansys, it's available for SimCenter and Femap. So we have this model which is done with beam elements, but some important details are also modeled with shells or plates. So if I'll switch off the thickness, you will see that important details are modeled with shell elements, and it's completely modeled in detail with taking into account on all the thicknesses. I will show the filled edges, how precise and beautiful this mesh is, and it gives us a possibility to recognize the welds on our model, and it gives us the possibility to have the most precise results of the fatigue calculation, which I will show you at the end of this session. It's also possible to do this on solid elements. There is, so sometimes we really require such a level of detalization, and we go deep into solid elements. However, for recognition of welds, we have a trick of putting the thin layer of shells on top of our solid model to be able, so they share the same nodes. They are able, so these nodes are transferring the forces and the stresses, and we're able to have the classification and recognition of welds on this. In this particular model, we don't have such level of detalization, but the plates are more than enough. And once again, it gives us an opportunity to have a beautiful presentation of the results. So, as you can imagine, this kind of structures, it is subjected to the huge amount of repetitive loading. It's actually this model, it has two trolleys on top and at the bottom. And to verify the fatigue, we need to collect a lot of data. We need to set up the loads in a certain way to be able to take into account the different conditions, working conditions and exceptional conditions of the crane, to take into account the biggest stress ranges, and to take into account the complete stress history of this structure. This slide demonstrates how many different loads are taken into account to this in this model. We have 13 different positions of the trolley on top. We have 4 more positions of the trolley at the bottom. They are combined together, but it's not only the live load. You should take into account the own weight. You should take into account the accelerations of gantry, accelerations of trolley, and all this load should be taken into account during the calculation of the fatigue. So this is the case where the SDC Verifier load combinations, individual loads, load sets, load groups, and load fatigue groups are coming into action, and helps us to represent the real behavior of the structure and to show you how it actually works. So we'll just show in Femap how many loads do we have in here. So we have gravity load, then we have the vertical load of the trolley itself in 13 positions and some positions of the trolley too. Then we have side loads of the same influences due to gantry acceleration. Then we have the accelerations of top and bottom trolleys, acceleration of gantry, and wind load, which is also automatically applied in Femap. So we have a tool which helps to define the direction of the wind, the pressure, and distribute this pressure over the full structure, taking into account drag coefficients, CV factors, and so on. So at the end, you see we have 73 loads, and now finally we go back to SDC Verifier. We're not going to cover the introduction into SDC Verifier interface and the possibilities of the software. It's completely covered in our previous sessions. So if you're not aware about what is SDC Verifier software, come and visit our website. There is a lot of tutorials and videos on how to get started with the program. So, but I want to stop on the calculation core and load combinations because it's crucial. So you can see that from our loads in SDC Verifier, we have in Femap we have grabbed them to SDC Verifier. We have all the same loads in here, and then we combine these loads in 211 different load sets for strength cases, for wind cases, and for fatigue cases, also taking into account empty trolley. SDC Verifier enables this possibility to combine the loads in linear way. I will show you the matrix of loading so you can edit multiple loads. And in this case, you'll be able to see this complete matrix where you see the different loads. So you have the loads in columns and then the combinations in the rows. And each row is taking into account loads with partial load factors and safety factors. And it also helps you to save calculation time by applying the unit load. And then if you need an empty trolley or you need a trolley with extra weight of the container, you just multiply that with different factor, which saves you the calculation time and the solution time. Taken into account in wind cases, but for fatigue, due to in the most standards, it's prescribed to calculate without wind influence, so on. So all this single loads are combined into linear combination with load sets, and then we go to the load groups, which are actually the envelope sets of results. So we combine all the strength sets with safety factor of 1.1 all together to see the worst results for strength. Then we do the same for wind. Then we have the same for storm, and we also have the fatigue in different groups. Taking into account the loads in different positions, we are able to prepare the fatigue groups where we have very precise distribution of cycles. So when you are creating the fatigue group and you're doing the fatigue summation calculation, you can take into account the amount of cycles for every part of the crane boom. So you can see here that we have group 7 where we have loads from position 13 to 6 and 14 to 17 on the second trolley. It's 100,000 cycles for this case, and then in some different areas there's different amounts of loading. So 13 to 6 in this area, we have 100,000 cycles, but then if we go back to from 11 to 6 we have another 400,000 cycles. So from here to here we add extra cycles because this is actually the area where trolley operates the most. So this helps you to combine all these loadings and to be able to set the realistic behavior of your structure. So this was all the preparation regarding the loading. It was done up front, but it literally takes you a few minutes to combine all this in a nice matrix. You're able to export this to Excel or import the matrix from Excel or modify it in here. It's easy. So you see we have 200 load combinations, but it's extremely easy to copy this and make 400 if necessary, and it helps you to handle huge amount of loading. One more preparation we need to do before we go directly into the fatigue calculations. We need to recognize the welds on our model. I already did this up front just to save time on this 30-minute session, but it took me about 4 minutes to calculate all the welds on our model of 450,000 finite elements. So coming back to Weld Finder, we already have all the welds recognized in this model on all the shell elements. We have more than 14,000 welds. And what I just want to do, so Weld Finder, everything you have to do so is to press find and wait about 4 minutes to have this, to have the complete welds recognized. You can edit them manually, you can modify, you can select by hand if necessary, but it's very precise. I did this recognition this morning automatically, and I just want to show you how this recognition looks like. So if I select all the welds and just press on the preview button, we will have a nice plot in Femap which highlights us all the welding. Not having the extremely powerful computer, I'm using my laptop, but still you can see here. So if we had a really great mesh and all the connections are automatically recognized and treated as welds. It takes it into account as a weld if there is the change in thickness, change in property, change in material, or the perpendicular connection or the connection of the certain angle. So we also have this beautiful node on top, and you can see that all the welds are completely recognized. You need to have a nice mesh and merge nodes, but that's it. After this, the recognition is completely automatic. And once again, if you have shell elements, it's possible to recreate a thin level of shells on top of your solids and have this recognition done also for solid models. So we go back to Weld Finder. That's basically it, what we had to do. So press find all the welds, preview if everything is correct. If you want, you can filter them by a certain value. You can go to the filter tab. And here you can preview, adjust something if necessary. We're just going to get back to the main window and finally proceed to the fatigue calculations. What I have done up front, I have prepared and calculated EN 13001 standard. So we will start from FEM. How easy and quick it is to add the standard in SDC Verifier. Basically, you execute the right click on the standards menu, go to add, and here you have a list of standards which are already implemented. So you see the ABS, AIC, API. We go all the way down different codes to different Eurocode codes. Let's start with FEM, which is the crane standard and one of the European standards for lifting appliances, highly used for this types of structures. So after I selected the standard wizard appears. It gives you the options you need to set up before you run your fatigue calculation. Basically, especially this one is quite simple. So we have to define several things, but yeah, it's literally 5 options. So what we have to do is select the entities on which you're going to calculate the model. We take the complete model, select all entities. By the way, this selector we do have here is going through the complete program. With this selection, you can select any part of the model, like properties, materials, selection based on the coordinate, or just select it manually in the main window of your FEA solver. So you can create this selection, then store it as a component, and after this, use this component for calculations, for plotting, for tables, reporting, and so on. So it's very handy, and this rule-based selector goes through the complete program, and you can keep the same selections in different areas of the program, in different chapters, and then prepare a report based on this. So what we do, we have recognized the welds, and now we need to set up the classification of welding. Basically, different standards are prescribing this weld classes. They are also called weld types or notch classes, notch cases. It defines the type of weld, the quality of weld, and it defines the sensor for the calculation of fatigue. So in the FEM standard, basically everything what is not welded, it's W0, and then you have K1, K0, K1, K2, K3, K4. The higher the numbers, the worse is the quality of the connection, or the more complicated connection it is. One more feature of SDC Verifier, it's not only recognizing the weld, but it also reorients the stresses into the weld directions. So what you can do, you can set up the different classification along the weld and perpendicular to the weld. You can also select your beam members, you can also define some complicated connections which you have modeled with beams, and set up the K2 for the complete beam member. So it's not only calculating on beams, it also on plates. It also does the same calculation on beam members. So we will repeat this specification very quickly. So for full model, we have W0. Then we have, it's already done, I believe. Yes. Then we apply another rule, and we select all welds. And for all welds, we want to have an X direction, and the direction along the weld, we want to have K1. We press apply, and it's done. Then we can copy this and define the type of weld for the perpendicular direction. Let's say it's going to be K2. Well, it should be a K2 perpendicular to the weld. And then we also want to define for shears. It's going to be K0 for shears. Once again, I go back to my weld types, select all welds, select the shear, and define K0. And also, well, when you have an intersection, in some direction, it's always perpendicular to the weld. So we need to define the separate classification for intersections. So we go to, we create another rule. We select all weld intersections, and for this weld intersections, we define the K2 along the weld. We do so, press OK. So this is quick classification. Now you can preview and plot it. So you can select all of this, press on this colored plot, and select the direction you want to plot. I just have a slide here. Not to waste time, we only have 10 minutes left. I have a slide here showing how the classification look like, so you can preview how the weld type is defined. What are we going to do next? We need to define the element group. Element group, according to FEM, is based on class of utilization and load spectrum. Load spectrum can be calculated. It also represents how frequently your structure is used with maximum load. So the higher the number is, the worse is the damage. And the class of utilization prescribes how many cycles do you have in your for your structure. So we're now doing the regular fatigue without a summation. So we're defining the class B7. It's 2 million cycles, and we define the worst. We're defining the P2. Let's say it's then. We have a table in standard, and on the intersection of this column and row, we have group E6. So we define the group E6 as the element group for our structure. We can also set different element groups for different parts of our model. I can add another rule here by pressing plus. And we need to define the material type. According to this standard, we need to set if it's 360 or 510, is it high-grade steel? We use the regular one. Sorry, we select apply to selected, or you can press to all. Okay. Then SDC checks if all of your materials are having the yield and tensile set properly. You can see for every property, every material, we have a nicely defined yield and tensile strengths. That's okay. And you can set up the safety factor for static stress check, which we're not doing now. We're pressing OK, and that's basically it. We added a standard. You can modify the input always, so you can modify these characteristics, classifications, and everything you do. And here we have 3 checks according to the standard. It's a static stress check, fatigue check, and fatigue summation. What do we have? In here, we have a possibility to completely preview everything what has been done. I mean, you can see the formulas. It's completely open. So, for example, we have a simple static stress check in here. If you press Edit, you can see the formulas. How is the allowable stress is calculated? It's taking the smallest of yield or tensile multiplied with 0.7, and then you have, based on this allowable stress, you have the stress in your element divided by this allowable value, and basically it represents with utilization factor if the structure is passing this simple check or not. You also have a fatigue check in here, so you can preview the formulas of fatigue. It's completely open. It's not a black box. And you can see it. You can even copy it, password protected, and modify, write your own rules based on this. So let's add another standard for running low on time. We go to Eurocode, which I promised to show you. It has a bit more setup, but basically it's the same. So we have members check. We have fatigue according to Eurocode. We select the fatigue. What do we need to define here? As well, again, we have the selection. We need to define the FAT class. It's slightly different. It's represent the fatigue stress. And yeah, well, the quality represents the essence curve and the FAT stress. You define the same for full model, and then you do select all the welds. I'm not going to stop detailing on this. You can build very complicated classifications like the one we have for EN code. You can set different weld parts, different quality, and so on. I will just define all welds, and for all welds in all the directions, I will give it a FAT class of 125, let's say. It's not a proper way to do so, but that's a quickie. Then we have this FAT class defined. We need to select, do we want to set the reduced range? All the classification in SDC Verifier, they also have the description. So you can take a look. What does this parameter means? When do you need to use it and how to define it? We're not using the reduced range in here. And then the Eurocode has this consequence of failure and assessment method. So based on this, the safety factor changes. If you have low consequence and damage tolerance, it's 1. If you have high consequence and safe life, it's 135. So what we have to do is basically we select high and let's say safe life, it's 135. We check again materials with yield is 0, everything is set, press OK, we have the Eurocode. And I already had the EN standard prepared because we also want to see the results. For my computer, it took about 20 minutes to calculate it, but because the model is huge and there's a lot of loading. So we can preview the EN 13001. We can also check the classifications and characteristics we had before. We can edit and go to the same wizard. Here it's slightly different. You can select the method. Is it the limit state or allowable stress design method? For this, you can set up the resistance factors, and also you have the same definition of notch class, which is the weld quality in here. And here you see this nice setup of different quality for different welds, and it also sets the different classification for the type of beam elements. It's 112 for all the directions of beams, and you can define the slope constant and reduced range. Do you want to use it? You can also use it for part of the model or for a complete model. And finally, you want to take a look on the results. How does it look like? I have just cleared the results by pressing OK. I hope I'm able to go to the results manager and open this results. Wait a second, I have stored these results within my computer, so it should be able to find it. If I select the fatigue and I select the results, check results, okay. Okay, Roman, can you help me to load these results? Are you sure it's stored here?
Yeah, you should have the check results directly in this folder.
Yeah, I have the check results and then the folder S1, but I don't see. I just select this folder, but nothing is loaded.
Make sure that you really the outcomes in this.
I do have check results in here, and here it is. How do I load that back into SDC?
You do the right way.
Okay, but if I select it here, nothing, so no results in this manager.
Wait, let me figure out what this one.
Okay, we're running low on time. I will include this load results, maybe this one, but this is just for the loads. Yes, done. Great. I don't know, I just had to press OK. Okay, sorry for this short delay. We will take 2 minutes longer just to preview the results. So I have loaded the results which I calculated before, and I can press preview on the plot. It will take a few seconds to read this result. But after this, as this is done, we will see the results. Meanwhile, I want to say that once again, this is a part of our month of webinars, and we will have 2 more sessions. In a week, we are going to show the example of offshore platform with beams, joints, and plate buckling checks. And in 2 weeks, we are going to present the part of the ship calculated with ABS and DNV rules on plates and stiffener buckling. So feel free to you're welcome to join these sessions. We will send you the invitation once again. There is no need to register again, but if you are not interested in this topic or you don't want to attend this, just decline this invitation and we will know that we won't send it to you again. And basically the calculation is done. So we have the result. We are able to preview. So we plotted the fatigue damage. We see that it's slightly overshooting in the boom area, but we are interested in plates. We are interested to see this result actually where we get into the detailed modeling. So we go in here and we see a nice plot of fatigue damage. And we really see that our classification of weld and setting the proper quality, the real quality of the welding gives us the best results on the welds. We really see this precise hotspots. We see the overshoots, and we are able to use this for maintenance of our structures subjected to fatigue, or present this during the review of new design or design modifications and any type of calculation that requires the fatigue analysis. So the next part of this would be going to the reporting and present a nice and beautiful report on how the calculation was done and how the results looks like with plots and tables. This is what I showed in our previous session, so you can take a look on that. Recording is on our website. And that's basically it. We prepared the setup for 3 different fatigue standards. We have calculated one of them. We recognized the weld. I hope I clarified to you the calculation core of SDC Verifier, and I showed the complete way of running the fatigue checks with SDC Verifier. One more thing I promised to let you know. We are working on increasing our database of standards. We are finishing the FKM, the German standard, which is one of the must, and we spent quite a lot of time on implementing this. We're now on the stage of final checking, and in next major release we will have the FKM standard, and we are also finishing the development of DVS. And I see the question from Gary, but I'm not able to. Petro, can you read this to me? I see that there was some question, but I will just finish. We are having the DVS standard, which is going to be also released in the next version. And basically, that's everything I wanted to show. I'm able to open the check. BS is on the list.
Yeah.
Thank you, John. BS and AS, Australian standards, we have quite a lot of requests, and BS, British standard, is in our list. It's probably not in this version, but I will put the priority higher for the version after this. But for now, we don't have it. But it's really not extremely complicated since we have all this template already ready. It's not very hard to to implement the new codes. So please, John, please send me an email, and I will share this with our developers to make sure that they understand the priority of this code. And Gary, unfortunately, I'm not able to share this model. I can share with you the record. I will share the recording, and I will be able to share maybe some part or other fatigue example, but not this one.
Okay, there was one more question about FLS code checking. How stresses are computed for FA model for FLS code checking? Hotspot method.
Hotspot method is not implemented yet. Also, it's in the list of development. I need to check with the guys if it's going to be ready to this release. We are calculating the stresses from the elements, and yeah, we are taking the nominal stresses from the elements for now. But hotspot method and rain flow counting are in the list, and it's also going to be released in the nearest versions, but not yet. Thank you for your questions. We are already running 5 minutes late. I hope I didn't take too much of your precious time, and I thank you for your time, for attending this, and I hope it was interesting to you. And if you're willing to use it, if you're willing to try it in your projects, if you want to have a trial version of the software, please hit me an email. I will generate a trial license for you. Our support guys are working from home now, having more time to help you, to run through the tutorials with you, to help you try the software or implement it into your engineering routines if you are